Hello, it's Yuste again. Welcome back to the Rasa Masterclass. This episode is part 2 of our deep dive into the training of NLU models. Previously, we covered how you can train your NLU models using the pre-configured processing pipelines. In this episode, we will dig deeper and look into the separate pipeline components, understand how each of them works, why are they necessary, and answer the most frequently asked questions about the NLU training data and how it affects the performance of your models. Let's go. First, let's quickly recap on what a processing pipeline is. In simple words, processing pipeline defines the NLU model, how user inputs are processed, which text features are extracted from them, which intent classification or entity extraction models are used to make the predictions, etc. A pipeline not only defines which components the NLU model consists of, but also in what sequence those components are trained and executed. Each component takes some kind of input and produces the output. The output of some components can later on be used by other components, but there also can be some components which produces the results that are directly added to the overall output of the NLU model. In the previous episode, we looked into two pre-configured Rasa pipelines, supervised embeddings and pre-trained embedding spacey pipeline. Under the hood, both of these pipelines consist of a set of components responsible for specific tasks, from text processing, feature extraction, to defining the actual models that are used to classify the intents and extract the entities. Let's take a look at all of these components step by step and understand them better, because once you learn what they do and why are they necessary, you will be able to create your own custom pipelines and make changes to the existing ones. Pre-trained embedding spacey pipeline starts with a component called spacey NLP. If you remember from the previous episode, this pipeline uses pre-trained word embeddings. Spacey NLP component is responsible for loading spacey language model and having it ready for the next processing steps. This component is only relevant if you are using spacey language models and is not necessary for other pipeline configurations. Next, regardless of the approach you are going for, using pre-trained word embeddings or learning them from scratch, your pipeline should define how user messages are processed. It's a very important step because for your models to learn the meaningful patterns, the examples they are trained on have to be split into smaller units. In Rasa, this stage is handled using a tokenizer, a component which takes user inputs in a simple, unstructured human language and splits them into smaller pieces, tokens. A token, for example, can be a word. There are a few tokenizers you can choose from depending on the approach you are using. If you're not planning on using pre-trained word embeddings, then the best choice for a tokenizer component is a whitespace tokenizer. How does it work? It looks for a whitespace in a sentence and creates a token for every whitespace separated character sequence. This component by default is used in a supervised embeddings pipeline and is suitable to process most of the languages. However, if you are building an assistant in a language which requires more specific tokenization, you can choose another available tokenizer or build one yourself. If you choose to use spacey language models, you can use a spacey tokenizer, which comes with the tokenization rules for the language models you are using. An important thing to remember about tokenizers in general is that since tokenization is one of the first processing steps applied on user inputs, a tokenizer component should be amongst one of the first components defined in your processing pipeline. The tokens created by a tokenizer are usually used by quite a few subsequent components in the pipeline. For example, an intent classifier, entity extraction component, and some others. Let's start with looking at the entity extraction first. To extract the entities, your NLU model needs a component for named entity recognition. Just like with all other components, Rasa gives you a few options to choose from. The most robust is a component called CRF Entity Extractor, which defines a model called conditional random field, which learns to identify which words in a sentence are entities and what kind of entities they are by observing the sequences of tokens. It picks a target word and looks at the surrounding words. It extracts text features from all of these words and, alongside provided labels, learns to identify entities in unseen user inputs. Those features are things like, is the target word a bias word? Does it start with a lowercase? What is the prefix? What is the suffix? Is it a digit? And so on. And similar for the surrounding words. If you want, you can also utilize part of speech features here, but for that to work, you will need a spacey library to be installed. A component CRF entity extractor produces the output which is directly added to the overall output of the NLU model. Which words in a sentence are entities and what are their labels? how confident the model was in making those predictions, and which model was used. If you have a small amount of training data and are using Spatie language models to boost the performance, you can use Spatie Entity Extractor, which will take advantage of known part-of-speech and other features to locate the entities in user inputs. You will notice that some entities you're trying to extract follow quite specific pattern. This applies to entities like dates, numbers, zip codes, and similar. You can enable your NLU models to extract such entities by using components like Ducklink HTTP Extractor, which allows you to leverage the power of Ducklink, a library specifically designed to extract information like dates, numbers, zip codes, phone numbers, emails, and some other information without training a named entity recognition model completely from scratch. We will get back to this topic a little bit later in the Rasa Masterclass. If you're dealing with more advanced cases of entity extraction where machine learning-based models are not enough, you can support the entity extraction of the CRF entity extractor by using regular expressions or lookup tables. Regular expressions match certain hard-coded patterns. For example, this is how you can match 5-digit zip codes. Lookup tables are useful when your entity has a predefined set of values. For example, an entity country can have 195 different values. To use regular expressions and/or lookup tables, add the regex featureizer component before the CRF entity extractor component in your pipeline. Regular expressions and lookup tables are adding additional features to CRF entity extractor, which mark whether a word was matched by a regular expression or a lookup table entry. Both of these components will add new features to the CRF model. However, the model is very likely to develop a bias for them. That's why you should be very careful when enforcing strict rules with regex extractors and use them only when really necessary. To summarize, Entity Extractor takes tokens as inputs and produces named entity recognition results, which are directly added to the overall output of the NLU model. The main thing you have to remember about specifying this component is that it has to come after the tokenizer. Now, let's talk about the intent classification task. To enable your NLU models to classify the intents, you initially need two main components, a featureizer and an actual model. A featureizer is used to create new features from the tokens, which then can be used by intent classification model to learn the underlying patterns and make the predictions. If you are not using pre-trained word embeddings, then a component called count vectors featureizer is a great choice for a featureizer component. It creates back-and-forth representation of your messages using sklearn's count vectorizer. Under the hood, it counts how many times distinct words in your training data appear in the message and provides that as an input for the intent classification model. In some situations, your models may work better if instead of counting words, it used n-grams, chunks of characters, to create the features. Usually, it makes your models more robust against typos, but at the same time, it increases the training time because the feature vectors get bigger. You can easily specify how the features should be created by customizing the analyzer parameter in your pipeline configuration. Once the features are created, they are good to be used to train the intent classification models. When you're not using pre-trained word embeddings, a component called embedding intent classifier is your best choice for the intent classification model. It is also recommended to use a count vectors featureizer alongside this component. In simple words, the features created by the count vectors featureizer will be fed into the intent classification model, and the results of the intent classification will be produced. So how does the model work under the hood? The embedding intent classifier embeds user inputs and intent labels into the same space. The supervised embeddings are then learned by maximizing the similarity between them, and the most probable intent is produced. The model also returns the rankings for all of the intents that did not win. I would like to highlight the strengths of this intent classification model once again. Since the model learns word embeddings from scratch using the data that you provide, it is way more likely to pick up domain-specific words. It also allows you to build AI assistants in pretty much any language that can be tokenized. And last but not least, it allows you to handle advanced cases like messages with multiple intents, which we will cover a little bit later in the masterclass. Now, let's talk about the situations where you are using pre-trained word embeddings. In cases like that, you should use a component called sklearn intent classifier for the intent classification. It defines a model called support vector machine, in short SVM, which uses the features extracted by the featureizer and those pre-trained word embeddings to learn the underlying patterns and predict the intent labels. The featureizer, which is usually used with this component, is called spaCy featureizer, which looks up those pre-trained word embeddings for each token and allows the models to learn the patterns and make the predictions. So, what's important to remember when specifying the intent classification components in your pipeline configuration? Since the intent classification component learns from the features extracted by the featureizer, a featureizer should always come before the intent classification component in your pipeline configuration. At the same time, since the featureizer uses the tokens produced by a tokenizer should come first before the featureizer. The intent classification component produces the results which are directly added to the overall output of the NLU model. This means that the intent classification component can be specified at the end of the pipeline or pretty much anywhere as long as the components responsible for the featureization and tokenization come first. Building custom processing pipelines and picking the components is a process, which will usually take you quite a few back and forth steps when building your models. It's also something you should always keep an eye on and make changes as your system grows. NLU training data in general is a crucial part when it comes to building good NLU models. The more training data you can have and the more you can learn about it, the better your models will be, and it will have a direct influence on which component should be included in your processing pipeline. So let's talk about the NLU training data a little bit more and start a segment which I will call Rasa NLU Data FAQs, where I will answer the most common questions Rasa developers have when creating the training data and training the models. Does the order of components in the processing pipeline matter? The short answer is yes. Each component in a processing pipeline is trained and executed one after another. Some components produce the output which is directly added to the overall output of the NLU model, but some components take the output produced by other components as input. For example, a named entity recognition component learns from sentences represented as tokens. Those tokens are produced by other component, a tokenizer. That's why a tokenizer component in the processing pipeline should always come before the named entity recognition component. Should I worry about the class imbalance in my NLU training data? Sometimes some intents in your NLU training data have significantly more examples than others. In machine learning, this is called class imbalance, and it's likely to affect your models and make them perform poorly. There are a few things you can do to go around this problem. One is that you should always aim to have more or less similar amount of examples for each intent. But in addition to this, there are some things that are implemented in Rasa to help you with that. For example, the supervised embeddings pipeline uses the balanced batching strategy. It tries to make sure that all classes are represented in each batch, or at least in as many subsequent batches as possible, still mimicking the fact that some classes are more frequent than the others. Does the punctuation in my training examples matter? Punctuation, like commas, exclamation marks, even emojis, are not extracted as tokens and therefore are not used as features to train the models. That's why the punctuation in your training examples should not affect the results of your intent classification or entity extraction models. Is intent classification and entity extraction case sensitive? It depends on the task. By default, named entity recognition is case sensitive. It takes tokens as they are and creates features based on that. But just like with pretty much everything in Rasa, you can specify that and change it if you want by tweaking the parameters of the model. Intent classification, on the other hand, by default is case insensitive because count vectors featureizer converts everything into lowercase. But again, if you want, you can change that by tweaking the parameters. I think some intents in my training data are very similar. What do I do? When different intents have very similar training examples, it's gonna be very difficult for a model to distinguish them. However, it's very important to be mindful when creating the training data because quite often a new intent is not necessary because examples can be modeled by leveraging entities. Imagine the case where a user provides their name or gives you a date. Intuitively, you might create an intent provide name for the message "it is Sarah" and an intent provide date for the message "it is on Monday." However, from an NLU perspective, these messages are very similar except for their entities. For this reason, it would be better to create an intent in form which unifies provide name and provide date intents. Later on, in your dialog management training data, you can define different story paths depending on which entity Rasa NLU extracted. What if I want to extract entities from one-word inputs? Extracting entities from user inputs which only consist of one word is still quite challenging. The best technique you can use right now is to create a specific intent, for example, inform, which would contain examples of how users would provide information even if those inputs consist of one word. You should label those inputs just as you do with any other NLU example and use them to train intent classification and entity extraction models. Can I specify more than one intent classification model in my pipeline? While technically you can do that, there is no real benefit in doing so, because based on how Rasa works right now, the predictions of the last specified intent classification model will always win. How do I deal with typos in user inputs? In real world, typos in user inputs is something you just cannot avoid, but there are a few things you can do to go around this problem. One thing you can do is implement a custom spell checker and add it to your custom pipeline configuration. It is a very nice way to fix typos in the extracted entities. Another thing you can do is to simply add some examples with typos to your training data for the models to pick up. Building good NLU models is a process, and there are quite a few things you have to keep in mind when building them. We will be going back to our NLU training data and configuration pipeline throughout the series as we add more and more features to our assistant. What NLU challenges have you encountered while building AI assistants? Let us know in the comments below, and I'll see you in the next episode of the Rasa Masterclass.